Hello friends, this is AKHILESH Pandeey and in this lecture, the network analysis lecture number 7, I will introduce you the topic nodal analysis. And in the last class we had discussed the topic mesh analysis, and before starting the nodal analysis I would like to solve one previous year GATE question related to the mesh analysis. So here is the question, and the question was asked in 2001 in 2 marks category, and this is the circuit given for the question, and voltage E0 has been asked in the question. Okay, so this is E0 that we have to find out. Now we can see that in this branch we have to find the current. Okay, so for finding the current we can apply the mesh analysis that we have just studied. And here we can the first step of mesh analysis is to analyze the all the mesh. So here we can analyze easily that in this loop there is no any inner loop. Inside there is no any loop. So it can be considered as a mesh. Again, this can be considered as a mesh, and this can be considered as a mesh. The second step to this is to assign the current to each mesh. So we will assign the current to each mesh. So in this mesh I am assigning the current I1, in this mesh I2, and in this mesh assigning the current as I3. Okay. Now in the first mesh what we can see, we have to apply now KVL to each of the mesh. Okay. So in the first mesh we can see that while writing the KVL we must know the voltage drop across the current source, but the current source is voltage independent, means the voltage across it can vary. We cannot determine the voltage across a current source. So here writing the KVL will be a tedious work. Instead we can directly see here that this I1 current is going through this branch, the same branch where the 8 ampere current source is. It means this I1 must be equal to this 8 ampere. So directly by writing the by assigning the I1 current in this mesh we can write I1 equals to 8 ampere because the same current is going through this. Okay, in which the current source is 8 ampere. Now come to this mesh. In this mesh, while writing the KVL, we will directly we can do, means I am assigning here plus minus again. Okay, so in the direction of I2, I have considered the drop across the resistance. So for this branch I2 is going upward and I1 is downward. So overall the current will be going, I2 will be flowing as I2 minus I1 in this branch. Now in this branch I2, in this branch I2, and in this branch what will be the current? I3 is going upward and I2 is going downward. So overall current in this branch will be downward, I2 minus I3. We can consider like this, I2 minus I3 going downward, I2 coming downward and I3 going upward. So overall I2 minus I3 downward. Okay. Now writing the current KVL for this mesh. So I am taking the polarity of the exiting one. Taking the polarity of the exiting one means if I am exiting from this element, so here it is minus, so minus I2 minus I1 into 10. This is the voltage drop across it. Now only I2 is flowing in this one, so minus again exiting one for exiting polarity, minus 2 I2 only because I2 current is there only, again exiting polarity minus 16, this is only the voltage source. Next minus 6, how much current? I2 minus I3, and that's it. We have put all the result, and so the KVL is over and equated it to 0. This is the KVL equation for this mesh. Again similarly we will write the KVL equation for this mesh. How we can write it? Again going through this, if I am going through this, so I2 minus I3 is the current drop in this direction, means in this direction. So this is the plus, so plus 6 I2 minus I3. If I am taking I2 minus I3, then it will be plus. Okay. If I am taking I3 minus I2, then it will be plus and it will be minus, because upward direction, in upward, if I am taking the current, then the voltage drop will be like this will be plus and this will be minus. But if downward there is a current, then this will be plus and this will be minus. So if I am circulating in this way and taking the exiting polarity, so this is plus and current into resistance, 6 into I2 minus I3. Next, plus 16. Next, here the drop will be plus minus because of I3. So minus 12 I3, exiting one, exiting polarity is minus. So minus 12 I3. Overall, this will be equal to 0. Exiting means the polarity at the when we exit this element, that is exiting polarity, what I am telling. Okay. So minus 12 I3 equals to 0. So we have these three equations and three variables, I1, I2, I3. I1 is already known, I1 equals to 8 ampere. By putting I1 in these equations, we will have two variables only, I2 and I3. We can easily find out I2, I3 from these two equations, and the result will be, the final result that we will get, I3 equals to, we will get 7 by 3 ampere. This is the desired value, means we need E0, so we desire I3 only. We are not interested in I2. So we will try to find I3 directly from these three equations. I3 equals to 7 by 3 ampere, and that I3 is flowing through this element. So E0 we can easily write E0 equals to 12 by 3. 12 I3 voltage drop. So 12 into I3, the value of I3 is 7 by 3, 3, 4, 12, 28 volt. So this is the answer for the question. So B will be the right answer. So this is very simple question related to mass analysis, and this type of questions can be asked in the upcoming exam. So we must practice some questions related to the mass, and it is useful in other advanced questions as well. So that's it about the mass analysis. Now I am going to the next topic, that is our topic in this lecture, and that is nodal analysis. So here it is, the nodal analysis. So in mass analysis, we had understood that mass analysis can be applied to the networks which are planar, but that is not the case for nodal analysis. The nodal analysis is instead applicable for both planar and non-planar type of networks. Nodal analysis is applicable for both planar and non-planar network. Okay, so this was the desired conditions for applicability of nodal analysis. Now we come directly to the steps involved in the nodal analysis. So first of all, I am having the circuit like this. Let's have a circuit first. So this is the circuit, this is voltage source, okay, this is again a resistance, this is again a resistance, this is again a resistance, whatever. Okay, this is R1, R2, R3, R4. This is some voltage source V. Now, for the nodal analysis, first of all, we have to determine all the nodes. Actually, the node is the point where more than two branches are connected. The node is the point where more than two branches are connected. If only two branches will be connected like this, then we will not consider it as a node. If there is one more branch, then only we will consider it as node and try to solve it. So for this given question, we can directly analyze that this can be a node because it has more than two branches. Other this two branch only, here only two branch, here only two branch, so this can be another one. So these are the two nodes that we have found. So the first step is to analyze all nodes. Analyze all nodes. We have analyzed that there are two nodes, this one and this one. Next step, what will be the next step? The next step is to assign zero potential, or you can say ground potential, zero potential or ground to one node. We have to just ground one potential or assign one node at zero potential. So either we can assign this node as on zero potential, or we can assign this node on zero potential. Mostly we used to assign the zero potential to the ground, means lower part of the branch as a zero potential, lower part of the node as a zero potential, so that we can means it's a visual thing that we used to assign the lower part as a zero potential, but it is your choice, you can assign this as a zero as well. So due to our convenience, we used to assign generally the zero potential to the lower part, and so we have assigned this as zero potential. Now the next step is assign voltage to each node, means to other nodes. One node we have reserved already as zero potential, and the rest remaining nodes will be assigned some voltages. Okay, so here we have only one node left apart from this, so we will assign one voltage source or one voltage level to it, and that we will assign V1. If there will be other nodes as well, then we would assign V1 this as V1, next as V2, and so on. Okay, so the third part is complete, the third step is complete. Now the fourth step, we'll have to write KCL equation at each node, or you can say each non-zero node. Non-zero node means the node that have zero voltage, we will not write KCL equation with that node. Apart from this, leaving that node, we will write the nodal equation, or you can say KCL equation for each other nodes. Okay, so here we have left with only one node apart from this zero potential node, so we will write the KCL equation for this node only. Okay, so how we can write the KCL equation for that node? So it's very easy. What the KCL equation means? KCL gives summation I equals to 0, means all the incoming or outgoing, the summation of all currents will be 0. The condition will be that if I am considering all the incoming current as positive, then I will have to consider the outgoing current as negative, and so on. So here I am taking the currents outgoing everywhere, means I am considering that in this branch the current is outgoing. So we have to just write the KCL at this node, means we have to find out the current in this branch, and current in this branch, and add all the currents and equate it to 0. That will be the KCL equation only. Okay. So first of all, the current in this branch, what will be the current in this branch? If I am taking this as I1, so V1 minus V upon R1. How we can write it? V1 minus V, because we are going through this one. V1, this is the voltage level, and here is a drop, V1 minus V, or we can see solve it by KVL as well, like V1 minus I1 R1. If there is a current through it, I1 is the current through it, V1 minus I1 R1 will be the drop, minus V, and finally we will reach to 0 point, so equal to 0. So we can solve it and get the V1 minus V upon R1. So this will be the result for I1 current. Okay, this will be the result for the I1 current. Similarly, we can get the result for this I2 current. What will be this I2 current? This will be the simple V1 minus 0 divided by R2. So V1 by R2. Simple it is. Again, for this I3 current will be what? I3 current will be V1 minus 0 upon R3 plus R4. So V1 upon R3 plus R4. So this will be the current These are the three currents that we have to find. We have already found. I1 V1 minus V upon R1, very easy. I2 V1 upon R2, simple. And I3 V1 minus 0 means V1 by R3 plus R4. So these are the currents, and summation of all these currents will be equal to 0. So we will have the equation like this: summation of currents equals to 0. So next step we will put the values of all individual currents. So V1 minus V upon R1 plus V1 upon R2 plus V1 upon R3 plus R4, and this will be equal to 0. So this is the KCL equation. We have written the KCL equation for all the nodes. If there will be so many other nodes, then we will write the KCL equation for all the nodes. Here we have only one node, so we are writing the KCL equation for single node. So this is the KCL equation, and by solving it we can easily get the result of V1, because V will be given in the question, R1, R2, R3, R4 all will be given in the question. So we can easily get the V1 using solving this equation. So in this way we can find the voltage at each node, and then after we can find the current through any element. So this is the process involved in nodal analysis. Now again there is some case where the nodal analysis fails, and what we can do in that case. So let's find where the case nodal analysis fails first. So when there is a voltage source like this, means let's take an example, plus minus V R, this is plus minus, this is R, and this is R, this is R resistance. Okay. So if we have the arrangement like this, so as for the nodal analysis that we have just read out, okay. So according to that, first we will assign all the nodes. So here we have this node, because this it has three branches. It has three branches connected to it. It has this will be considered as a single node, okay, because at the single point it is being connected. There is no any element in between these all. So this is like a connection at a single point, okay. So we have 1, 2, 3 nodes here. Now the next step will be to the ground one of the node, okay. We have set it as ground. Next, at these two nodes we have to apply the KCL. When we will try to apply the KCL at this node, so we will have to find the current through this, current through this, and current through this, okay. This current can be found easily. V minus, if we assign some voltage source, V1 minus V divided by resistance. This current can be easily found that V1 divided by whatever the resistance value it will be, okay. But what about this voltage source? Means if we have to find the current through this, so we know that voltage source is current independent, means the current can be anything through a voltage, through a voltage source, okay. So through a voltage source the current cannot be determined. Through a voltage source current cannot be determined, and so here determining the current will be very tedious work. Means we cannot find out the current, and ultimately we cannot apply the KCL here. Similarly, we cannot apply the KCL here. Then what we will do? So if there will be such case that in between two nodes there is a voltage source, so we will not use the nodal analysis there. Instead we will use the super nodal analysis, and super node we will consider. Means by combining these two nodes we will consider these two nodes as a single node. These two nodes as a single node, and to this single node the current, all the currents are going outward. If I am taking this current is going I1, I2, I1 going in this branch, I2 going in this branch, I3 in this branch, and I4 in this branch. So for this super node we will sum all these currents, means I1 plus I2 plus I3 plus I4 equals to 0. And finding I1, I2, I3, I4 all are easy. We can easily find the values of I1, I2, I3, I4, because if we will get some voltage V here, means we will assign V1 here, and if this voltage source is 2, so we can write that this point, this node will be V1 plus 2. If this is V1, this is 2 volt, then we can easily assign this node as V1 plus 2. And if we have the voltage at this node, then we can easily write the current through this branch and current through this branch. So I1 and I2 is known. Again, similarly, we can, if we have V1, then we can easily find I3 and this I4. So all the currents we can find out easily, and by finding all these currents, we can apply the KCL at this super node. Okay, because through from this super node, these branch elements are connected, so all outgoing currents will sum up to 0, and that's why I1 plus I2 plus I3 plus I4 is equals to 0, and then we can easily derive the result for the V1. So wherever the nodal analysis fails due to this reason, due to the voltage source connected in between the two nodes, then in that case we will apply the super node concept, and this was the super node concept. Now we will see one question, one previous year question related to the nodal analysis, and that then we will end this lecture. Okay, so here is the question related to the nodal analysis. And the question was asked in 1998 in 2-mark category. Okay, sorry. This was in 1 mark, 1998, 1 mark. And the figure was, this is 1 volt, this is 2 ohm, again 2 ohm, 1 ohm, and this is 3 ampere. Okay, that's it. This is A, this is B. These are the 2 points or 2 nodes, you can say A, B. Now what we have to find? We have to find the voltage across terminal A and B. A and B is, and the options are 0.5 volt, 3.0 volt, 3.5 volt, and D option is 4.0 volt. So this is the question from the previous GATE exam, and we have to find the current, the voltage across this terminal. Okay, so we can directly apply the nodal analysis here, and in the nodal analysis we have understood that the first step is to find out the analyze the nodes. So here we have a node and here we have a node. So 2 nodes we have assigned it. Now the next step is to ground one node. So we will ground this node, writing B here. Okay, we will ground this node. Okay. Now the next step is to assign the voltage level to other nodes. So I am assigning V voltage level to this node. Okay. The next step will be what? Next step is to write the KCL equation at the nodes. So this is the node that we have left. So we will write the KCL equation at this node. So V minus 1 voltage drop divided by resistance 2 plus V upon 2 plus, okay. So in this branch, instead of writing the current equation, or you can say current value, we can easily analyze that this 3 ampere is coming inside, coming inwards to this node, coming towards this node. So these are the outgoing currents. I have written this current as outgoing, I have written this current as outgoing, and this is incoming current. So this will be written in minus 3. So minus 3 equals to 0. This resistance will be of no use, equals to 0. The next step, we will solve the V by 2, so it will be V, and 1 by 2, in that side if we will take, we will get the V equals to 3.5 volts. So this will be the correct answer. So very simple question related to the nodal analysis, and this type of questions can be asked in the upcoming exam as well. So this was all about the nodal analysis in this lecture, and I will come with some other topics in the next lecture. So thank you so much for watching.